Right, okay, let's continue our excursions into integration. You have seen the definition of indefinite and indefinite integral in the previous lectures through the Riemann sums and through the antiderivatives, and then we connected them together. Then we went through some basic integration operations that follow from the definition largely, like things like linearity and elementary rules for integration. Again, it is much easier to integrate by the table than it is to do it from first principles. And the biggest difference between differentiation and integration is the differentiation is algorithmic. That is, you can train a monkey or a computer to do it, but integration isn't. So it is, to an extent, all of art. And up to about 100 years ago, when you take a new class of integrals, that was worth some of the publication. These days, it's mostly machine algebra systems we will see one at the end of this lecture. So today we go through the more advanced methods to make you able to integrate like a boss. And the reason for that is quantum mechanics, when it eventually arrives, it begins with a triple integral, right? So the observables in quantum mechanics are integrals of wave functions, variously transformed, and since we just happen to live in a three-dimensional space, the dimensionality of those problems in real life begins at 3. So actually the simplest possible calculation in quantum mechanics involves a pretty horrifying integral. So it is absolutely imperative that you are all able to integrate with your eyes closed. Okay, so the first item on the agenda is what's called integration by substitution. And it occurs in situations where it's not obvious how to integrate some horribly nested expression. Let's say we have something like this. It's an integral f of phi of x dx. And a good example would be something like this. So an integral 1 over 1 of phi plus x to the fourth dx. There is no table rule for this, and it is clear that this is a superposition of two simple functions that we do know how to integrate. One is 1 over root of something, which we would have been able to integrate if we thought just that, and the other is a polynomial, so 1 plus x to the fourth, which we also know how to do. But here we have this composition, and we now will look at ways of disentangling such composite objects. So, a theorem that states the principle of integration by parts if f of u and u equals phi of x are both differentiable, and the antiderivative of f of u is f big of u plus constant. So let's say we are able to integrate the outside function, then the following is true. An integral f of phi of x, phi prime of x dx is f big phi of x plus a constant. A fairly obscure statement at this point, like some horribly complicated integral looks like the antiderivative of our composite function. Well, let us first formally prove this obscure statement, and then we will actually look a bit inside it, and then it will become clear how to actually use it. So, well, let us just differentiate both sides. So if we have f of phi of x prime, well, that's just a chain rule, so f prime phi of x, phi prime of x. But by our assumption this is the antiderivative of the small f. So this is actually f phi of x, phi of x, which is exactly what occurs under this integral. So if we take the derivative of both sides of this, on this side we will get that, and on that side we will get f prime, and so we have now demonstrated that the two sides are in fact equal. Okay, so this is again something that would not necessarily immediately click. This is just a fairly abstract exercise in pushing symbols around. So let me give you 3 different examples, and then we can refer back to this generic structure. So again, if you just sit and wonder what this is and haven't understood much of what I said, I didn't either when I was your age. So let us go through the examples and then this will become clear. Alright, so the first one is example 1 integral 3x plus 4 to the power 5 dx. Now, the long way around here would be to open up the fifth power and take it term by term, but we'd rather not do that. What we would observe is if this was just y to the fifth dy, well then we would have easily taken it because we know how to integrate powers. However, we have something fairly basic underneath and something fairly basic outside. So we can try and disentangle it using that. Okay, so we have our f of u, so our f is the fifth power. Our u is 3x plus 4. Why don't we make that substitution? U equals 3x plus 4. Now we need to translate 2 things here. One is the expression itself, which would be easy enough because this would just be u to the fifth. So that goes integral u to the fifth. But then, of course, the next thing we need to translate is also dx, because that's the little length element, or area element, or volume element, and that needs to be translated into u as well. So not just do we need to calculate the u, we need to calculate its differential. du is 3 dx, as you know, because you have had some practice with calculating differentials, right? So the derivative of this times dx. Therefore, dx is 1/3 du. And we can now do that substitution over there. So this will be 1/3 du. So that is an integral 1/3 in front u to the fifth du. And now that we know we've got an integral of function of u with respect to u, we know how to take it. So this will be 1/3 times 1/6 u to the 6th plus a constant. So 1/18 u to the 6th plus a constant. And the last thing we need to do is to reverse the substitution. We put the original function there. 1/18 3x plus 4 to the power 6 plus constant. So we did 2 things here. We looked at the original integral, and we realized that under the integral we had a superposition of 2 simple things that we do know how to integrate. We made a substitution, and normally what you would do is you would look at the thing here. It's a philosophical principle, not terribly precise, but it works. You would look at something that you would not rather have. Something that you would rather have collapsed into a single variable, and in this case 3x plus 4 is as good as anything. So we declare that a new variable. We then need to replace that with the new variable, but importantly this dx is also transformed as a result, and so we need to calculate du. it will depend on dx, and then we can use to substitute that back. When we make both replacements, we arrive at an integral that we do know how to take. We take that integral, and at the very end, we reverse the substitution. Now, the more eagle-eyed of you, those who had further math and so on in school, would simply remember that as a standard rule, that if you have a linear function under there, just don't forget to put 1/3 in front. I've done it the long way, and this kind of explains where the 1/3 is coming from. It's the relationship between the differentials here. Let's now go to a more complicated example where such a visual integration directly would not have been possible. So, example 2. Integral x root 1 plus x squared dx. Here, it's utterly unclear, right? And no matter how much fiddling one would put in, it's not possible to algebraically transform it into something that would reduce to a table integral. What would we rather not have here? Well, this 1 plus x squared sticks out. Why don't we make that a new variable? So, u equals 1 plus x squared. And then we will have that integral, that root of u. But then what we also need to do is we need to transform the differential, so we need to calculate du. Well, that's u prime dx, and so this would be 2x dx. And then we need to replace that, and we need to replace dx. Dx is du over 2x. So this is like a little cut in. So that becomes an integral, x root u, and then dx is du over 2x. Thankfully, x cancels here, and most of your problems would be of that kind. They are redesigned to be elegant. If you are integrating something and it suddenly exploded into half a page of mathematics, check everything if your problems are designed to be solvable. Absolutely not the case in real life. I have seen my fair share of horrible integrals which I've wasted days on, and then just thought, okay, stop it, and evaluated them numerically. I will tell you how to do that in the next couple of lectures, but in this case it cancels. So we have a half integral root u du, which we do know how to tell, how to take. But perhaps people would not be immediately comfortable with taking the integral of a root, but you are all comfortable with taking an integral of a power. So why don't we rewrite it as a power? So a half integral u to the power 1/2 du. And so when we add 1 to that, that would be 3/2. So that's 1/2, 3/2 to minus 1, so 2/3, and then u to the power 3/2 plus the constant. Cosmetic simplifications, so u to the power 3/2 over 3 plus the constant. And finally, we need to reverse the substitution, because our u is 1 plus x squared. So this is 1/3, 1 plus x squared to the power 3 plus the constant. Now, in this case, it actually makes sense to check. That is, that's a long enough and complicated enough chain of transformations that we'd rather be assured that what we've just calculated is real. For that, we need to differentiate this back and hope that we obtain this expression under the integral. So, 1/3, 1 plus x squared to the power 3/2 plus a constant prime. Okay, 1/3 gets out, 1/3, then chain rule, power 3/2, we get 3 halves in front, the power becomes 1/2 times the derivative of whatever occurred in front, that's 2x, and the constant just disappears in differentiation. 3 cancels, 2 cancels, x 1 plus x squared to the power of 1/2, which is exactly what we had under the integral, except the power 1/2 was as an explicit root rather than the fractional power. Okay, and this is generally a good idea. Every time you evaluate an indefinite integral, just differentiate it back to make sure that there are no errors in that. An even more complicated example, this one with explicit limits. So an integral, so example 3, integral from 0 to 1 over 4x plus 5 to the power of 4 dx. Now, we have an additional complication here in that we have the limits. Now, these limits refer to the original variable. When we substitute the variables, we will need to transform the limits correspondingly. So, notes in here. What sticks out? Well, 4x plus 5 is kind of inconvenient because we do know how to integrate the power minus 4. So our u would be 4x plus 5. du is dx, and therefore dx is water du. However, what we also need to know is what is u at x equals 1. So u of 1 is in this case 9. And then u of 0 is 5. And when the integral becomes an integral du, these should be the new limits. So, doing the substitution, integral 1 over u to the 4th dx is a quarter du, and the limits are from 5 to 9. Quarter gets in front, integral from 5 to 9, u to the minus 4 du. So that is a quarter, 1 over minus 3, and then that's u to the minus 3 from 5 to 9, and that is minus 1 over 12, and then 9 to the minus 3 minus 5 to the minus 3. After you do all the horrible arithmetic, 1 by 1 over 2, 7, 3, 3, 7, 5. A cosmetic notice here, unless your problem setting explicitly involves floating point numbers, do not convert the answer into floating point numbers. So do not evaluate this. Keep it as a rational number because this answer is exact. But if you do it on a calculator, inevitably you will get an approximate answer, even if it's to 16 decimal places. There are subtle differences in, for example, numerical computing between analytical and floating point numbers. Generally, it's a good idea to preserve the type. Okay, so for this substitution business, this is what the procedure is. And now perhaps you can understand better what I've been talking about here. We have some outside function and the inside, and this inside we would rather not have. We call it u, and then we know the integral of the outside function. But of course our actual thing is nested, and so this, so if we take this phi out and make it actually u to match the notation, here, 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 and you would notice that this is actually du, and this is what we were calculating in those square brackets. So this is a generic formulation of the procedure wherein we replace what we don't want to have, but we also must modify the differential to match the replacement. So in any actual practical calculation, it is reasonably straightforward to see what we do. Great. So that's substitution. You will have plenty of practice in your workshop. The other mainstream method for integrating horrible combinations of things is called integration by parts. It's quite possible that you've been given that formula, but you probably were not given the proof when you were doing it at school. So we will now prove it. So the formula itself has the full and complicated form, then it has an easily memorable shorthand, and it also has a derivation. So the full formula is an integral from a to b of u of x b x dx is equal to u of x b of x calculated at the limits from a to b minus integral from a to b u prime of b of x b of x dx. Now, how can something like this possibly be used? Let us think about it. If we have this integral and u is a part of whatever occurs underneath it, which becomes simpler under differentiation. For example, when u is x, under differentiation it would simply disappear. So we'd rather actually differentiate. And then d prime is the part of that expression which we know how to easily integrate. And so if we were to transform that into this, where the prime is shifted, well, that's an integral of b prime, and that's the derivative of u. If b prime is easily integrated and u is easily differentiated, then perhaps that result will be a simpler expression. It will become a bit clearer in the examples, and this we simply need to drag around. That's just a number. Now, a slightly easier way of writing this relies on the fact that this is actually db, and that u prime of x dx is du. We can write the shorthand for arbitrary limits in the following way. Integral u dv is u v minus integral v du. So that's actually a lot easier to memorize. And unfortunately, integration by parts is important and ubiquitous enough that I will require you to memorize this. It is unavoidable. You know, the Homo sapiens in the 21st century is supposed to remember the formula of integration by parts. I mean, if you remember the history of the Star Wars universe, you will remember integration by parts. It pertains to our universe, and therefore it's probably more useful in practice. Okay, let us prove this. What I will do is I will take the differential. So u of x, v of x, and I will calculate the differential of this object. Well, just a product rule. So the derivative of that is u prime v plus v prime u. So what we will have is u prime x dx dx plus u x dx. That's just differentiation. And then what I'll do is I will integrate both sides of this expression from a to b. So, a little bit closer here. Put an integral from a to b, integral from a to b, and an integral from a to b. This integral here is trivial. Right? Integral dx is equal to x. Integral df is equal to f. Integral d horrible square bracket is equal to the horrible square bracket. So therefore that, on the left hand side, u x of x just from a to b. You can lay this one. And then this we just leave. So I will move that over there, minus integral from a to b, u of x b prime x dx has to be equal to whatever's left, integral from a to b, u prime of x. Maybe I should move them around the other way, so I'll move that over there. So this is u prime x. Yes, well. U of x, u prime x dx is an integral a to b, u prime x dx dx. And finally, if I just flip this around, what we get is integral u of x u prime of x dx is u of x dx from a to b minus integral from a to b u prime x dx, and that's exactly the same as what we have there. So take the product, calculate the differential, integrate both sides, turn the equation around, and we have the proof here. Okay, all becomes considerably clearer when we go through the examples of how to actually integrate using that expression. So that will be example 4. And we got an integral x e to the x dx. Now, no amount of fiddling or substitutions here would produce any progress. However, remember the philosophy that I told you. In this case, x is something that becomes simpler on differentiation, and e to the x we can easily integrate. So we can say that u is x, and then du therefore is dx. Then our dv is e to the x dx, and v is just e to the x. So here, in this mnemonic shorthand, u is x, and dv is e to the x dx. We find the u, we find the dv. From dv we can calculate the v by integrating it, and from u we calculate du. So all of the things on the left hand side we know, all of the things on the right hand side we have calculated within that square cut in. Therefore, uv is e to the x times x, there, minus an integral ddu. So e to the x is v, du is dx. Notice that the pesky x has disappeared. from under the integral, which we now know how to take. So plus a constant here because we have already partially integrated this. So this is x e to the x. The integral of e to the x is just e to the x. X plus a constant. Again, it is a very good idea to differentiate this back because these are non-trivial transformations. X e to the x minus e to the x plus a constant prime product rule here. So this is e to the x plus x e to the x. So a prime b is just the exponential. A b prime, this doesn't change, x e to the x, minus, this doesn't change, e to the x. Two exponentials cancel each other. So that's x e to the x. As required, this is what occurred under our original integral. So the answer is correct. Okay, have I got, yes, so an example where the limits are explicit, when we've got a's and b's, you simply use the full formula and substitute all the limits and this Newton-Leibniz difference as well. So example 5. Integral from 0 to pi of x cosine x. Same problem in that this is not a table integral, however same solution in that individually x is easy to differentiate and cosine is easy to integrate. So what we say is u is x, du is therefore dx, dv is cosine x dx, d is therefore sine x. We are integrating, therefore no minus. And then what we have is a uv, so x sine x computed from 0 to pi minus integral v du, integral to 0 to pi sine x dx on the upper limit. This is equal to, if memory serves, sine of pi is 0, right? So on the upper limit this is 0, on the lower limit this is also 0, so just 0 minus integral sine x dx is minus cos, so plus cosine x from 0 to pi. Cosine on the pi limit is minus 1. So minus 1 minus cosine of 0 is 1. So the answer is minus 2. Once again, look at the expression. Identify the part that will become simpler on differentiation. That is your u. The rest of it will be dv. Do the transformations as per that formula there. One foot in front of the other, simplify the mathematics, you get the final answer. Okay, so these are the two mainstream methods, as it were. There's one more method that is sometimes useful. You occasionally get into situations where the expression is so complicated that this integration by parts makes it simpler but doesn't actually reduce it to anything directly integrable, in which case you have to integrate it by parts again or do a substitution and so on. Let me give you an example. For example, something like that in is an integral x nth power e to the ax dx. So it is an integral with respect to x, but it depends on an index n. If we now integrate this by parts, what we will get is u equals x to the n, dv is mx n minus 1 dx, then dv is e ax dx, v will be 1 over a e ax, and if we get that integration by parts formula, so uv x to the n over a e x minus integral du, so 1 over a, and that's v and that's du, so n here, x n minus 1 e to the n x dx. Notice that this is actually I n minus 1. It's the same as I, except the index got reduced by 1. And therefore we get the following expression. In is x to the n over a e to the x minus n over a I n minus 1, which is a recurrently defined sequence. I0 is easy to calculate because the x would not occur. It's just the exponential integral. So you know A0. From there you can compute I1. From there I2. From there I3. As you can see, the formula will become more and more complicated as you go. So I10 would have a huge number of terms in it. And it's just one of the ways of taking these things. This is called a recursive definition, a recursive solution to an integral. Occasionally, this becomes necessary. Right, so all of this in practical chemistry is actually quite academic. I told already the group that comes to my classes that the only time I actually do integrals by hand is in these classes. You need to know how to do it, but in practice the cost of a mistake for a chemist is sufficiently dramatic that one needs to have some assurances that actually the calculation is correct. Okay. So this is Mathematica. Download and install it. The university has a site license. There is this input palette there. And well, let's just put some horrible integral into there. So we will have, and let's start with indefinite integrals. Something that's non-trivial, like 1 over. In my handout, I've got x to the 4th minus some variable a to the 4th and dx. This is a seriously complicated integral that will take about half an hour to crack through the necessary substitutions, and it's an inverse trigonometric function if memory serves. And if we do that, we see in milliseconds. We can actually time it, I think. Timing. Yeah, so the time is so short it couldn't measure the calculation of this. But you can see arc, tangent, and log, and so on. It would have been quite a story if we were to do it by hand. Let's now calculate some definite integral. So an integral from a to b of sine x squared dx. Well, that's your integral, and of course this doesn't really matter what power we have. Mathematica will do it 2019 times by parts in this case, and eventually if it doesn't crash and run out of memory, we'll reduce the console. So when we launch the task manager, we will probably see it running. So here there's the call from kernel. So it's using one core of our CPU. And there we go. So it is big, large output. Okay, show more. Show even more. Right, so that's actually about 3,000 terms. At the risk of crashing the computer, let's ask it to show all areas. That will be a few pages of integers, but that is the integral of sine to the power 2019.
Will that do the test?
Not likely. And then something even more complicated where, you know, multiple instances of integration by parts would be necessary, but let's take an integral from minus infinity to infinity, so that involves first indefinite integration, then Newton-Raphton's formula, and then you would have to take the limit of something seriously non-trivial, 1 over 2 plus x squared times the square root of 4 plus 3x squared dx. Yeah, faster than you can blink. That's a hyperbolic arc cosine of 3 halves. Internally, it uses horribly generalized functions for this integration. Sometimes people ask, you know, why doesn't it tell us how we did it? That's because we don't want to know. It's not a table integration of any kind or any simple algorithm. It translates things into generalized hypergeometric functions for which all integrals are analytical and translates it back. And if it manages to do it, then it has computed the integral. So it is all fairly complicated. Right, so we will have our entire next lecture will be about Mathematica, about differentiating, integrating, multidimensional plotting, you know, uncertainty propagation and so on using symbolic algebra systems. So you will see more of this in the next lecture. And from there, it's just the numerical methods and then it's pretty. Any questions?